Alright, ladies and gentlemen, today's class recording has started. So the other class wanted me to really start doing it more like a YouTube channel. So I'm going to say, hey everybody, before we get started, yeah, like and subscribe. leave a comment. It really helps the channel out. So tell your friends.
Turn the post notice on.
Yeah, exactly. I believe somebody said I should say ding the bell so that
Follow the Insta at Magic Lens.
Down here in the description.
Okay. So before we get started, before we continue on with our drawing, let's go to the first page of the outline. Right? I told you that we were going to skip Roman numeral number 1 because we were going to fill it out today as sort of a review activity. So first, the title of the presentation here is called Location of Electrons in the Quantum Mechanical Model, but location is in quotation marks. Why is location in the quotation marks? It's not exact, right? Based on whose principle are we not exact? Who said we can't know the exact location of an electron? Heisenberg, right? Heisenberg's uncertainty principle says we can't know exactly where an electron is and how fast it's going at the same time, okay? Now, we can't know exactly, but what do we know, or what can we sort of predict? Where it's been, and based on where it's been, we can predict where it might be, right? So what do we call those areas of high probability? Orbitals, right? Who's responsible for an atomic model that has orbitals? Schrodinger, right? So Schrodinger comes up with a mathematical equation that allows us to identify the location of where electrons were previously, which lead us to areas that we can predict they will be in the future. We call those areas orbitals. Okay? Good? So, Jordan had a question about the last question on the left, right? It was asking you about the difference between Bohr's orbits and Schrodinger's orbitals. What is the difference between an orbit in the Bohr model versus a orbital in Schrodinger's model? Go ahead. No, okay. Okay.
I don't know.
No, you're on the right track. It's not quite far enough there. Not quite. What did Bohr say about his orbits? What did Bohr say about his orbits? They're shells. And what had to be true about the electrons? Oh, good. There's no in between, right? It's definitively on this spot or this spot or this spot, right? Is that the case with Schrodinger's model and the orbitals? No. What do we talk about with Schrodinger's model and orbitals? What does an orbital represent? An area of high what? Probability, right? An area of high probability of finding an electron. But where could an electron actually be? Anywhere, right? But there are certain areas of higher probability where they are, we call those orbitals. Okay? There is one thing that Bohr's model and Schrodinger's model do have in common, and that's the idea of quantization. Do we remember what that idea means if we say that energy levels are quantized? Okay, so, go ahead. Good. based on the location of an orbit or the location of an orbital, that tells us how much energy electrons in those orbits or orbitals have. Okay? That is something that they have in common. Which orbitals or orbits have electrons with the lowest energy? Closest to the nucleus. And as we get farther and farther away from the nucleus, electrons will have more and more energy. That idea is similar between Bohr and Schrodinger, but the idea of, does it have to be in an exact defined location, or is there an area over which we can look at? All right? So, let's fill out Roman numeral number 1 on the top of your paper, right? The work of Heisenberg and Schrodinger lead us to the conclusion that the exact location of an electron can never be known. Okay? Schrodinger's wave equations reveal areas of high electron density or electron probability, right? Although we don't know for sure, we have a good idea of where we can most likely find an electron. And these areas of high probability are referred to as orbitals. All right, ready to go? Yesterday, we started working on our model of an atom showing electron orbitals, okay? Here, this small black dot at the origin of the x, y, and z axis is going to represent what? That's going to be the nucleus of the atom, right? Compared to the rest of the stuff, how big is the nucleus? Very small, right? Nucleus basically exists at the origin, and that's it. So now we start putting in orbitals, right? So the first orbital that we put looks like this, okay? What did we say about this orbital at the beginning? Okay, good. Low energy. It's a solid sphere, right? Solid sphere. How big is it? Pretty small, right? And close to the nucleus, okay? So low energy, small, close to the nucleus, spherical, okay? Next orbital that we put up on the drawing looked like this. Ooh. Okay? So, what about this orbital? So like the first orbital, the yellow orbital is inside of this one. So is it a solid sphere? It's a non-solid sphere, or we could say it's a hollow sphere, right? Okay. Okay, that's fine. You can say non-solid sphere. Okay. Okay. It's a hollow sphere. What else do we say about this orbital? A little bit bigger, right? What does that mean if it's a little bit bigger? A little bit more energy, right? Okay. What else though? How it's similar because it's what? It's red. But it's also it's still hollow. It's still spherical, even though it's a little bit bigger. Okay. All right. Next, 3 orbitals that we put on looked like this, looked like this, and looked like this. Okay. As far as a general shape goes, we sort of describe these as what? Kind of like an hourglass, right? Skinny in the middle, wider out on the sides. Okay. What did we say about the energy of these orbitals? A little bit higher than the sphere, but if we look at the shape and the distance of these 3 orbitals compared to each other, they're the same. Okay? One's on the x-axis, one's on the y-axis, one's on the z-axis. Why would they arrange themselves in that fashion? They're symmetrical, right? we said there were two things, or two sort of principles that govern the shape and the location of these orbitals. What are the two things that electrons are sort of trying to accomplish or trying to do? Close to the nucleus, but far apart from each other, right? If you have one orbital on the x-axis, the farthest the next orbital could be from it would be on the y-axis, right? If it's tilted a little bit, it's going to be closer on one side than the other side. Yes? Are we following me on that one? Right? Okay. Then the third orbital, right, the z-axis, we said comes straight out of the board. That's as far as it can be away from the other two, right? So having them arranged on the x, y, and z axis, that's as far apart as they can get from each other. Okay? All right. Next one that we drew looked like this. Okay? So hopefully we're starting to see a pattern developing here, right? What's the pattern that we're starting to see? Hold on a second. Do we have any hourglasses in this picture to share? Okay. I did. Okay, but let's go with this first, right? Okay. What happened to the orbitals from here to here? Okay, it got bigger, right? Let's talk about it in terms of our picture. What did I do when I changed from the previous orbital to this orbital? Changing color. Every time we change color, what's the first shape that we draw? Circle, right? Or spherical, right? Okay. Every time we change color, first shape we draw is a circle. Okay? Jack, after we draw our circles, what's next? Hourglass. Now we have our hourglasses, right? So there is another hourglass this way, right? How many red hourglasses did we draw?
6.
Well, technically, how many hourglasses did we draw? 3, right? The hourglass has 2 parts, the top and the bottom. That's one whole section. So here, just to kind of reiterate that, when I go up here, look, ready? See, these are connected. This is one orbital. Okay? Yeah. Power of technology. Right? That's one orbital. So the hourglass is one orbital. Even though it looks like 2 separate things sort of stuck together, that's one complete orbital. Okay? What do you think the next shape we're going to draw is? Another hourglass. Where's that hourglass going to go? Y-axis, right? And then where's the next hourglass going to go? Z-axis. Okay? So again, we start seeing patterns here. Now, that being said, if you understand the pattern, maybe you don't have to draw all of them because it starts kind of messing your picture up a little bit, right? Okay. Yeah, that's right. So even we're going to draw the picture first, then we'll start going back and naming parts of the picture. It does kind of look like a turtle and a turtle. Yours does. All right. So the next one gets a little bit confusing because when we went from yellow to red, the first thing we drew was a circle, okay? But then when we went from yellow to red, we added the new shape, we added the hourglass, okay? When we went from red to blue, the first thing we drew was the circle, the sphere. Then we drew the hourglasses, but with a new color comes a new shape, okay? Now, this one's going to be a little confusing for starters, but then let me show it to you and then we'll go, okay? So, the next shape looks like this. Okay? It is the same color. Okay, so no, first, let me move it, okay?
So it's like 2 hours.
I kind of refer to it as butterfly, but dragonfly could kind of work too, okay?
Or 2 hourglasses.
Now, see, now we don't want, so this is the thing we have to keep in mind, right? Even though this looks like 4 separate locations, this is all one orbital, okay? So this butterfly or this dragonfly is all one orbital. Now, let's go with some reductive or some brain power. Let's just go with that, okay? If the objective of an electron is to get as close to the nucleus as it can be, but still far away from other electrons, where would this dragonfly show up? In between what, Sanchez? In between the hourglasses, right? So if there's an hourglass on the x-axis and an hourglass on the y-axis, there's a dragonfly between the x and y axis. Okay? Does that make sense? Where else could there be a dragonfly? If there's a dragonfly between the x and the y axis, x and z axis, y and z axis. Okay? But those are all true, but there are other shapes, and we'll talk about what those other shapes are in just a second. Okay? So now go ahead and add your dragonfly here. Okay, are we going to go with dragonfly? Is that cool? Like, okay.
We're not calling it a fan.
Major, you can call it whatever you want, Major.
No, fish is not a thing.
The thing we have to remember, though, is that that is all one orbital. Okay, that's all one orbital. Even though it looks like 4 separate lobes. Okay. Now, if you're getting to the point where your drawing is getting a little too messed or a little too crowded, that's what we have the small ones down on the bottom for, right? So if you want to draw your dragonfly sort of in that down, or down in that one of the small ones down there, you can do that, okay? So this dragonfly, this blue dragonfly, right? As we're watching the video, just make sure that right, this blue dragonfly goes in between the x and the y axis, and there's other ones between the x and the z axis, and there's other ones between this y and the z axis, and there's actually a couple more, and we'll talk about what those are because they're hard to draw, and they just make your drawing look crazy. As if it doesn't look already crazy enough. Again, things we have to remember here, right? These are all based on locations of electrons in the past, right? We've seen locations, or we've seen electrons in these spots previously, so as a prediction, we will predict that they will show up there again in the future. Good. No. So kid, you will not have to draw this whole picture. You might have to draw individual parts of the picture. Like if I say, draw me a p orbital, we'll learn this in a second. Draw me a p orbital, you're gonna have to draw an hourglass. Or draw me a d orbital, you have to draw me a dragonfly. Like so, yeah. You won't necessarily have to draw the whole picture. And one of the things that we're going to get into, maybe tomorrow, but definitely on Monday, is this drawing is too complex for us to use like on a daily basis. So there have to be simpler ways for us to represent what this drawing is showing us, and that's what we're going to get into tomorrow and Monday. All right. I'm only going to draw one dragonfly because it gets a little bit too hectic. Yeah, hectic is a good word. Okay. All right. Ready for the next one? We only got 3 more to do. Okay. All right. Here we go.
Wow. It's a new color. No, that is
it a new color?
Yes. I'm using
green circle.
I'm using
okay.
green, so it's kind of
Don't, yeah, because that was just another dragonfly that I threw in there. Okay, like so. Yeah, don't worry about that. Drawing one dragonfly would be good. Okay, so, but
is it like the biggest symbol?
Sure. Well, every new. Okay, so first there's a color change, right? What's the first shape we draw every time there's a color change? A circle. But that circle encompasses all of the other stuff that was drawn before it. Yes, Kenneth, go ahead. The other dragonfly? I know, don't worry about that. Like, if you understand the idea that the dragonflies exist between the X and Y axis, and the X and Z axis, and the Y and Z axis, that's the important part. Adding that extra dragonfly might get a little bit really confusing as far as your picture goes.
Oh, so this is the biggest hollow sphere containing everything with the most energy.
I feel like I have to get through this and not run.
It's facts.
Okay, you can draw another one if you want to.
Well, I don't know.
It's facts.
Right now, don't. Okay. If we after we start talking about them in a little more detail, if you think you need to draw another one, then you can go back and do that. Okay. But so first, there's a color change. Every time we have a color change, what's the first shape we draw? Sphere, right? Okay. And that sphere covers everything that was drawn before it. Okay. What do you think the next shape that we put on this picture is going to be? Be an hourglass, right? What color is that hourglass going to be? It's going to be green. How far out is the hourglass going to go compared to the circle? A little bit farther than the circle, because hourglasses go a little bit farther than the circle. Oh, that was a point that I forgot to make for it. If you notice the dragonflies, right, you can still kind of see the dragonflies underneath the screen, right? The blue dragonflies are a little bit bigger than the blue hourglasses, right? Well, I wanted to make it dramatic enough to show that they were different. Well, the green circle is going to be definitely bigger than all of them.
Oh, okay. So that's okay.
Yep. And then, right? The next one is a green hourglass. That reaches just a little bit farther out than the green circle. As long as you understand that it's,
Mine just looks like a background, just like little.
it's okay. That's why you have those smaller ones down at the bottom that might help us, like, highlight or identify individual parts of this drawing. So, not necessarily that you have to draw them all, because now it might get a little bit too complex, but how many green hourglasses should there be? There should be 3 green hourglasses. One on the x-axis, one on the y-axis, one on the z-axis, right? So again, if you understand that there are 3 hourglasses, you might not have to draw all of them. Okay. Like I said, the big drawing is going to get a little bit convoluted, right? It's going to get a little bit messy. Is that okay? Convoluted is just a fancy way of saying it. So, diluted is like bigger. Right? So, a diluted version of this drawing would just be if you only drew one of the green hourglasses, because you understand that there's 2 more, but they're on the x-axis. So diluted would be like a lower version or like a weaker version of this process. I think I'm not going to add another color. Okay. Yes. Yeah, we'll get that. So, okay. Yeah, that's right now you don't understand any of this, so like why we're doing any of this, but there is a reason why, and we'll start getting into that here in just a second. Okay. All right. I've drawn it. I'm going to add it, but you guys don't have to add it if you don't want to. Okay? We've added a green sphere. We've added 3 green hourglasses. What's going to be next? Butterflies or dragonflies, right? But they're still going to be what color? Okay? So this one, I decided not to fill them in because
It's something.
it's not.
That's my dog's something.
Right? There's my dragonfly shape. Yes. Okay. But notice, color, still green. Right? Even though it's just a green outline, it's still green. Okay. Butterfly or dragonfly shape. And how far out does that dragonfly shape go compared to the hourglasses? Just a little bit farther. Okay? Yeah. Say again. Yeah, like I mean, they all sort of start in the middle, Sophia, but they can't really all go there because there's already electrons in that space. You know what I'm saying? But technically, they all sort of start in the middle.
Can I like do that in a slack or something?
If you want to, or if you just want to do it in green outline, like I did, you know, you can just do it because it's still green though. Like that's the important thing to remember. Like it's still green. Okay? Even though I didn't fill it in, I made it in green. I made it in green pen because it's still green, and that's important. Okay? This last shape that I added, this one, right? It's in green. It's in green marker. Like the outline of it is green because it's over the hourglasses, and it's over. But remember, our butterflies or our dragonflies go in between the x and y axis. They're not on the x, y axis in the way. They're in between. Okay? Sort of splitting the difference there.
No, ew. I don't think something.
You are not being graded on the neatness of the drawing.
I need to.
All right, so science, right?
I love science.
Make observations, look for patterns. There are 2 things that we can use to classify or to distinguish all of these orbitals from each other. What are the 2 things that we can use to sort of classify these or distinguish all of these orbitals from each other? Color, size, and I guess there's a 3rd thing then. Shape, right? Color, size, and shape. Although, no, color, size, and shape, okay? All of these orbitals, all of these shapes that we've drawn on the board, we can classify them according to color, size, and shape, okay? The color changes as we go how? Farther away from the nucleus. We keep changing color. So what is the color going to represent for us? Good, right? Wow. Patterns. Yes. Well done. I'll give you credit on the recording. That was Maggie that came up with that. All right.
Right.
So, okay. So
Hey, you tell them, Maggie.
the color of our orbital represents something that we call the principal quantum number. Okay? First, this is principal, P-A-L, right? Okay? Like there's principal P-A-L and principal P-L-E, yes? Yes? Okay. The principal is your pal, right? Okay? So when we talk principal this way, right? When we talk principal P-A-L, that means like the highest or the most important, right? Okay? So the principal quantum number. First, we use a lowercase letter n to represent that principal quantum number. Okay? And, just like Maggie said, it represents, for the most part, how much energy electrons that are in those orbitals contain. The higher the principal quantum number, the more energy electrons have in those orbitals. Okay? Good so far? Okay. Orbitals closer to the nucleus, ones that have lower principal quantum numbers, have electrons with lower energy. All right, good there? Okay. So, if we go back to our main drawing, right, the first orbital that we drew was what color?
Yellow.
Yellow. What will be the yellow orbital's principal quantum number? 1. The next color orbital that we drew were what? Red. All red orbitals will have a principal quantum number equal to 2. Next color we drew was blue. All blue orbitals have a principal quantum number equal to 3. And then all green orbitals have a principal quantum number equal to 4. Okay? Alright, good job today, everybody. Good progress. We will pick it up from there and talk about the size and shape tomorrow. Okay?